Wow, from researching today's topic, I can certainly see why so many people are thoroughly confused by hard drives and what all those names mean. Let's get together and resolve this once and for all, and to do that, I'm going to simplify data storage devices by looking at two main things: protocols and interfaces. As a bonus, please stay to the end for a chart listing all the different protocols and interfaces in an easy to understand list of which drive you should be looking at for your system. Hey, it's Steve here, helping you make sense of your computer. If you're new to this channel, please make sure you click that subscribe button down below. Now, to descramble this mess and to make sense of the misinformation that is out there, the first point is to understand the different protocols or communications drivers for hard drives. These are what the device uses to communicate with the system. The BIOS or UEFI, which are two different types of motherboard firmware, are typically programmed for the particular protocol, and then the operating system looks for a similar driver to communicate. There are three primary protocols for consideration, leaving RAID out of the equation for this video. First up is from 1994 and is IDE, or Integrated Drive Electronics. This is the first point of confusion, as people often refer to ATA drives as IDE drives, but IDE is the protocol and ATA is the interface. AHCI is Advanced Host Controller Interface from 2004. AHCI can process one command queue with 32 commands per queue and has a latency of 6 microseconds. If you are using SSD, make sure that AHCI is selected in the BIOS and not IDE. Keep in mind that AHCI was developed primarily for mechanical hard drives, in other words, those with spindles and platters. Next up, we'll have a look at the new kid on the block, which is NVMe, or Non-Volatile Memory Express, from 2011. This only works with PCIe-based drives. Just like a SATA drive uses AHCI to communicate with the computer system, PCIe drives need to rely on a host controller called NVMe. This protocol was developed for SSD drives and takes the SATA interface, with all of its limitations, out of the equation. NVMe can process up to 64,000 command queues with 64,000 commands per queue and has a latency of only 2.8 microseconds. Keep in mind that with some motherboards, you need to disable CMS in the UEFI BIOS to get the M.2 drives to work optimally. But in all cases, check with your motherboard manufacturer for specifics. From protocols, we switch to the interface of the various hard drives. We'll look at the most common types in use by the majority, so others like SCSI, EIDE, SAS, and M.SATA, which was for notebooks, these are not commonly used, so they will be ignored for the sake of this video. ATA, or Advanced Technology Attachment, is from 1986. This is now also known as PATA, or Parallel ATA, and has a 40-pin connector and cable. An 80-pin cable was also used, but the connector was still 40-pin. ATA was renamed to PATA to avoid confusion with SATA. ATA drives integrate the controller directly on the drive itself and can transfer up to 133 megabytes per second. SATA, which is Serial Advanced Technology Attachment, came out in 2000 and uses a 7-pin connector. SATA was developed for mechanical hard drives with rotating magnetic disks. SATA 1 was rated at 150 megabytes per second, SATA 2 300, and SATA 3 a massive 600 megabytes per second, all over one lane. These are traditionally 2.5-inch or 3.5-inch drives. The next evolution was SSD, which is solid-state drive. They use flash memory instead of rotating mechanical disks. Here we have the first major issue with SSD, as they initially used the AHCI protocol, which is limited to 600 megabytes per second. Introducing the M.2 or second generation interface, formerly known as an NGFF, or next generation form factor. Although the drive format is different, the motherboard connection is still SATA and uses the SATA AHCI protocol, so its performance is identical to a regular SSD SATA drive. M.2 drives presently come in 3 tiers: SATA, PCI Express 2, and PCI Express 4. If we look at the M.2 SSD, the most common format sizes are 2230, 2242, 2260, and 2280. There are others like the 22110, but it is not at all common. To understand these numbers, the first two are the width, and the second two or three numbers are the length in millimeter. And to really confuse the issue, the NAND flash memory on these drives can be SLC, eMLC, MLC, TLC, or quad level cell, QLC. TLC is the most common as it is the cheapest to manufacture, but has a low read-write cycle lifespan. If you're looking at servers, consider drives with eMLC, which will last 4 to 6 times longer than TLC. The next interface is PCIe, or Peripheral Components Interconnect Express. Now you can have a half-height, half-length PCI add-in card, which is a way to connect the M.2 drives to a motherboard that does not have an M.2 connector. PCIe Gen 2 is 500 megabytes per second per lane, up to 16 lanes, and PCIe Gen 3 is 1000 megabytes per second per lane, up to 16 lanes, and PCIe Gen 4 is a massive 2000 megabytes per second per lane, up to 16 lanes, so in other words, 32 gigabytes per second. Bear in mind, these are theoretical maximum throughput rates. PCIe Express 4 supports one key, Key M, and uses 4 PCIe lanes. The main types of M.2 connectors are B key, which are 6 pins to the left of the gap. This configuration supports PCI X2 connections. Then there is the fastest of them all, the M key, 5 pins to the right of the gap. This configuration supports PCIe X4 bus connections. But the most commonly keyed M.2 drive is the B&M key, which uses both gaps with 5 pins to the right of the card and 6 pins on the left. Because of the physical design, B&M keys are limited to PCIe X2 speeds. So, to summarize and provide the chart as promised, let's take a look at an overview of things. As an example, a 500 gigabyte SATA 3 7200 RPM drive will transfer a maximum of 150 megabytes per second, and a 500 gigabyte SATA SSD drive 600 megabytes per second over AHCI. Currently, the M.2 NVMe PCI 3 X2 drives can transfer a maximum of 2 gigabytes per second. There are a few M.2 NVMe PCIe 4 drives on the market that are rated at 4 to 5 gigabytes per second. So as you can see, all these names and numbers can really confuse things. Hopefully, this video has helped shed a little bit of light on it to make it easier for you to understand. If you like the content of this video, give us a thumbs up. And of course, stay tuned for our next video